Hello and welcome, and thank you for joining this webinar on the new version of BOSfluids. BOSfluids 8.0 introduces some new improvements, various new capabilities, both big and smaller. The new version of BOSfluids is, by the way, already available for download for all users through the software portal. So some of the new major features in BOSfluids 8.0 are support for the NFPA analyses, that is part of the firewater module, an improved flood and drain model, support for reciprocating equipment, addition of PIPENET interface, and improvement of other interfaces, extension of the features of various special flow elements, and many more smaller improvements for the user interface and also internally to make things run smoother for you. So the first thing I want to show is the new firewater module in BOSfluids. So the firewater module is available as an add-on license to your BOSfluids license, and it consists out of new analyses and new elements. So it provides new element types like the Deluge Nozzle, sprinkler and surfaces, and new analysis types like NFPA, firewater coverage, and flood and drain. So you can, in the features, also hide and show the features related to the firewater module. So if you would do that, they are no longer visible under the analysis and element settings, as well as fields related. So I also hit the structural analysis features, for example. That will clean up your user interface a bit. But let's turn it on again. So the new analysis types, or the new analysis type related to the firewater module, is the NFPA analysis. So the NFPA analysis brings you a way of performing a static flow calculation, and that flow calculation optimizes a certain minimum flow rate for a sprinkler. So you specify a supply node. So for instance, in this model, over here is my my water supply, and that will provide water to these sprinkler rings around this tank. And the NFPA analysis lets you perform a analysis where you make sure that all nozzles, or the most remote nozzle, will receive the minimum amount of flow. You can also specify a supply curve, meaning that you will, if you have like a pump or something that has a known maximum supply static pressure, you can specify that over here, and the flow rate, etc. So related to this NFPA analysis, a friction model is applied that is different from what is typical in BOSfluids. So the typical friction model is the Darcy-Weisbach friction model. However, the NFPA prescribes that you will use the Hazen-Williams friction model. So, and that is what this analysis does, as well as the velocity pressure has been taken into account according to these rules by the NFPA. So performing this analysis will also give you the results we'll show later, and a report that is related to the way the NFPA prescribes the report should look like. So that's described in the NFPA 13 and 15. So the other analysis related to the firewater module is the firewater coverage analysis type. So this again uses optionally the same friction models as being used by NFPA, or the standard Weisbach can also be selected. And what this analysis does, it will calculate the amount of of a surface that is being covered by the firewater. So each of these sprinklers cover a certain area, and you can calculate what will be the firewater flux, so how much water will be transferred from the sprinkler to the surface. And of course the NFPA also has some regulations about the amount of water that each surface should see. And the third analysis related to the firewater module is the flood and drain. So that's typically being used for rapidly flooding an initially dry firewater system. So that's a transient analysis, so things will change in time. A valve can be opened and the empty system can be flooded with firewater until each of the sprinklers has been reached and all the air has been pushed out of the system. So this firewater, the flood and drain analysis is also can also be activated separately from the firewater module add-on. So in terms of element types that are being added, so the firewater module provides these new type of elements. So the deluge nozzle, sprinkler, and surfaces for the firewater coverage. So the deluge nozzle is basically an inlet-outlet which also provides options for letting in and out gas. So it's a gas nozzle which is being used if you have a, for instance, a sprinkler. The sprinkler element itself that's based on that deluge nozzle, but it also has different options. So, for example, the pressure loss can be specified as a K factor. So typically for sprinklers, the manufacturer provides you with a data sheet with the spray factor, with the pressure loss as a K factor. So that K factor is a measure of the pressure loss. The typical in BOSfluids is the discharge coefficient, which should be used for valves, for example. And that can also be specified optionally. But the default is the K factor. So for a sprinkler, you can also specify minimum pressure, a maximum pressure, and a minimum flow rate. So we'll look at the results in a moment where these parameters will be taken into account. Of course, that minimum flow rate is used by that NFPA analysis type, which makes sure that each of the sprinkler receives its specified minimum flow. So for the area coverage, you can specify a spray profile for that sprinkler. So the spray profile, you can specify a custom profile where you specify the radius on versus a distance, or you specify just a conical spray profile with an angle and a maximum distance. This spray profile can also be visualized, like for example over here. You'll see which part of that surface is already being covered without running the analysis yet. So you can use these viewer button to activate that spray profile and deactivate it again. And the other elements are related to surfaces. So different kinds of shapes, like a cylinder, a rectangle, or in this case a pylon, which is being used to model the roof of this tank element. And with that, you're very flexible in creating all kinds of surfaces where your firewater coverage is being analyzed. So, for instance, also if you have like different kind of pipes or features, you can use these surfaces because they also block spray that's, for example, being sprayed if there's something in between the surface you want to wet and the sprinkler. Yeah, these things can also block certain parts of your firewater coverage. So that's specifically what you'll aim to do with this analysis type. Also, for the piping, so if you click on a pipe, so like I said, so that NFPA analysis type that also performs the friction factor with the Hazen-Williams method, and for that you'll specify a C factor, so that's basically a resistance factor for that Hazen-Williams calculation. That's optionally now available for your piping to calculate that resistance in your piping. So if I switch to the results, so let's first start with the steady state results. So this is the NFPA analysis. So that NFPA analysis optimized my supply pressure such that all the sprinklers in my model see the minimum flow rate, and here there are additional data sets available which are called relative flow rate. So the relative flow rate is a measure of the flow with respect to that minimum flow that was being specified earlier with the sprinklers. So you'll see that in this case the NFPA analysis made sure that each of the sprinklers are seeing its respective minimum flow rate. So the minimum flow rate is depicted as being 0. So if I double click on that element or that data point in this data set, you'll see that this particular sprinkler sees the minimum of all this flow rate, but is still above the minimum flow rate, just above that minimum flow rate specified. So 0 being the minimum of specified flow rate. The same for the pressure. So that's also a new data set, relative pressure. So relative pressure also means 0 means the minimum pressure, while 1 means the maximum pressure. So when you have every sprinkler, in this case, between the minimum and maximum pressure, there are values between 0 and 1. And you see that in this case, all these sprinklers are in between 0 and 1. So these relative pressure and flow data sets are also available for regular steady state analysis if you specify that minimum or maximum pressure for your piping elements. So let's move on to the firewater coverage analysis. So that's over here the type surface. So here you see that for the firewater coverage analysis, the firewater flux has been calculated. This data set shows you the coverage of each of these sprinklers on the surface. So in this case, the tank surface being modeled as a cylinder, and the roof as a pylon. And also the NFPA prescribes, for example, a minimum fire water flux of 10 liters per minute per square meter. So you would be able to, for instance, specify 10 over here, and you see all the each of the areas that receives that minimum amount of 10 liters per minute per square meter. Let's put it back to global. So when we go to the transient analysis, so this is the flood and drain analysis. So for instance, over here we have a valve opening, and after that the water spreads through the fire water system. If I use the time slider, you'll see how the water will go in your system. And if you, for instance, check the pressure at some points, you'll see that it can have pretty high water hammer effects, especially when you have like two water columns in a ring that collide with each other at the end. That will result in a water hammer and a surge traveling again through your system, giving you pressure peaks in your model and in your system. So that is definitely something. It's what's important to analyze, and which can be done with this flood and drain analysis. So that flood and drain analysis type that was already existing in BOSfluids has been improved for this new version. So there were various improvements, like the gas flow through fittings, like for example valves that are not completely open, or check valves, etc. That's now being modeled more accurately, where also the pressure drop, or the friction of the gas moving through that valve, has been taken into account now. So previously it was neglected, as typically like air has like 1,000 times less dense than the liquid. But especially for valves that are not all the way open, which can happen, for example, with check valves, or yeah, just regular valves which are not opened completely. That may have an effect, and that's now more accurately modeled. So also things like choking, so of course the air being compressible, when you have critical flow going through your valve, that means yeah, you can have choking effects in that valve, and that's also now being taken into account. So your results are definitely more accurate now. So let me also show you the report. So the new report that has been added related to the fire water module is that NFPA report. So if I open that report, you'll see that BOSfluids generates that NFPA report for you, and that's the way the NFPA specifies the report should look like. So for example, you have this graph where the supply of your water as being put against the demand of the sprinklers. So you can find where your flow rate or your supply should be for meeting the demand, and also all these sprinklers in your system are located. So this is pretty big system, and all the necessary yeah, output values according to the NFPA are listed in this report. So so that's about the firewater module. So if you're interested, please contact us, and we can provide you also with a trial for yeah and demonstration if you want more info on this firewater module. So the next thing I want to show you are some improvements for the file import interface. So starting from a blank BOSfluids model, you can import the model from various file extensions. And new is the PIPENET file interface, where you can load a PIPENET file, which of course is being 2D schematic, but that you can review of course in the 2D view of BOSfluids and extend to being 3D. Next, there are some improvements for the PCF file interface, so the piping component file. So opening, for instance, these large number of PCF files from one model, almost 2000 files over here. You have now new options to group the different elements in that model. So both item code and symbol keys. So the item codes and symbol keys are often used to depict some specific type of fitting, like a specific valve. This makes it much easier to identify them and add some relevant information if applicable. So if I continue and load this this model, so it's quite a large model. So I will change to the wireframe mode at first, so you can more clearly see the extents of the model, almost consisting out of 32,000 elements. So it's over here. Let's zoom in to a specific region. We can switch back from the wireframe mode to the normal mode, and for instance, all these fittings, if applicable, and having a specific symbol key, those are now grouped. So for instance, the symbol key for this this valve over here, VV star star, might mean some specific type of valve, and the information for that can be easily adjusted by going to that specific group in the elements and changing all the valves that are part of that specific element group. So that makes your PCF import interface even more flexible and easier to use. So now I would like to show you some more new elements types that have been added to BOSfluids. So the reciprocating pump and the reciprocating compressor were added. So the centrifugal pump and compressor were already there, but they have now been extended by also the recip versions. So reciprocating equipment typically produces pulse-like flow in your system, and specifying the typical dimensions of the equipment of the cylinder, like this has been done here, allows BOSfluids to calculate that specific flow pattern in time. And this being transient package, you can also specify a transient event like a speed curve, like a transient startup, for example. So if we go to the results for this small model, you'll see that we have an operating speed increased from 0 to 1000 RPMs. And if we, for instance, take a look at the discharge flow rate, you'll see the the typical flow pulsations that are associated with reciprocating equipment, which in this case grow in time as the pump starts up. So you see a whole bunch of new data sets associated with that reciprocating equipment over here. So of course, reciprocating equipment, you often perform also pulsation analyses, which can be done in our other package, BOSpulse. Well, in BOSpulse, you'll typically more focus on the pulsation and the shaking forces. This now also allows you in BOSfluids to perform a surge analysis, which can be important if there are any transient events happening. You can also study that now in BOSfluids, and to aid that, we have implemented a new internal file interface, or a new internal file structure, I want to say. So that makes it easier for you to open a BOSfluids file in BOSpulse and vice versa. So if you're more interested in BOSpulse, we have also a release webinar on Thursday. Another element that was already there, but we extended search vessel. So for the search vessel, you can specify a type, so closed vessel or an air vented vessel, and you can specify the initial state, both from from steady state or from installation. So when a search vessel is being placed and it has a pre-charge gas pressure inside, this makes it easier for you to specify those conditions than previously was the case. And also this field is new, the maximum gas volume. So for bladder type search vessels, for example, of course the gas volume cannot become bigger than the search vessel itself, so the air cannot leave that vessel. You can specify that max gas volume, and whenever the bladder extends or expands to the full volume of the search vessel, it basically shuts down this search vessel and stops the flow, the volumetric flow into this piping. Right, let's open this model with air valves. So for an air valve, we also extended this element type with a flow rate curve. So a flow rate curve allows you to specify how the flow changes with the pressure. This also allows you to specify air valves that are not non-instantaneous opening and closing, like for example triple function air valves. So both through the flow rate and the previous option through the discharge coefficient is of course also possible. Alright. So coming to the flow solvers. So we also made improvements in the flow solvers. One thing I want to highlight are the improvements we did for the cavitation models. So cavitation, meaning the formation of vapor whenever the liquid drops below the vapor pressure. So that's typically goes with the formation of vapor bubbles. So that's something that is pretty tough to capture in a 1D flow package. But these default models, which are present in BOSfluids and in other packages as well, they are mainly aimed at the column separation. So for instance, when you have a closing valve, downstream of the valve, you will pull a vapor cavity behind the downstream of the valve. where the pressure drops and a vapor cavity starts, and whenever the flow or the pressure recovers, that that cavity collapses again, and it gives you a pressure peak, so a pressure surge in your system. So that's the typical application of those cavitation models, but there are of course other ways these below vacuum conditions can occur. So this is a picture which shows you the front side view of a piping. So this is a high point over here. Whenever you have a high point and the vapor supply, the supply pressure will drop, you'll create a vapor cavity at the highly elevated points. And what BOSfluids already had, it was a model to let those vapor cavities grow even when they would span multiple cells, so they could grow. But for this particular example, where you have like a very small flow going from left to right over here, so there's so the initially there's a flow here, so the vapor or the pressure drops away. You'll start creating this vapor cavity over here, and these bubbles will the cavity will grow. But what would happen in the previous versions of BOSfluids is those bubbles would be transported downstream, where they would form continuously here and collapse there, giving you a very chaotic behavior. Well, there's actually these bubbles have buoyancy, and they will rise, and they will actually that cavity will grow actually from the top, and it's called slack flow, and there's still liquid going from left to right here. So this has been improved in this new version of BOSfluids, where this vapor cavity actually starts growing from that top elevated part, and will grow in this direction, and eventually we'll also be able to recover from that direction again. So that is especially something that that can be very beneficial if you have this specific event happening in your system. So to conclude, I want to show you some of the smaller improvements we made. Hopefully they will come in very useful for you. So so the first thing I want to show you is the initial flow boundary condition. So this is a new flow boundary condition type. So if I have this situation where you'll typically encounter where you have one end, like this outlet of a system that's known, it goes to atmospheric conditions, but the inlet you don't really know. It comes from a reservoir or from a pump or something, and it gives you an unknown pressure over here, but you do know what the operating flow rate is. And that, of course, is very important. If you have like a transient vent where this valve will close, you'll need to have that flow rate and the velocity correct. So what you would do is you will create a steady states analysis. You put in that flow rate, and you'll get from that analysis the actual pressure over here, and then you'll start a transient analysis where you'll change this boundary condition from flow to a pressure boundary condition, and that will correctly have you calculate that water hammer event. Of course, you cannot leave that as a fixed flow, because if that flow were truly fixed, you keep on pushing that flow into this system, even though this valve would close. And that would just blow up your pressure in the system. So that's typically not what happens, especially if you come from a reservoir, then that flow is not fixed. It will drop, as soon as you close that valve, but you will keep that supply pressure over here. So now we have this new flow boundary conditions called initial flow. So what that will do is it will basically do that manual steps you had to do automatically for you right now. So it will put in a fixed flow condition in the steady state. From that flow condition, from the results, the steady state results, it will change that to a pressure boundary condition and have that supply pressure in it for the transient analysis. So if I just run that transient analysis with that initial flow and go to the results, so you'll see it will start with a fixed flow of 200 cubic meters an hour. But then if I click on that supply node over here, you see that as soon as this valve starts to close, your flow actually will drop, and it will have some pressure waves going through your system and flow waves as well. But it will change to a fixed pressure, which we can see if we change that to the pressure data set. You'll see that we have a fixed pressure from the start of your transient analysis. So that saves you from a couple of steps. So another small thing we've added might come in useful. So alright, I want to select this valve over here, but I was still in this tab for nodes. If you just left click on the element just for a second, it will automatically now change to that element tab and select that valve for you. And vice versa also, of course, if you want to have this bend over here selected, just click on it for a second and it will change to your correct node tab, and that will hopefully save you some seconds, which just makes it everything a bit smoother. So another thing I want to show you is the addition of some new data sets. So let's say we have our analysis settings over here. So not sure, maybe you have known that before, so it was already there. So you can select which data sets you want to include in your analysis. So for instance, if you want to have additional data sets or want to reduce your output data, so yeah, your file size of your output data, you can deselect or select some of these data sets. And for this new version, we have added some more data sets. They're not by default on, so you can turn them on over here. So the static pressure and the total head and the hydraulic head. So especially these head data sets. So many engineers working in process flow use also the pressure not in actual pressure in bars or psi, but in head. So in a measure of elevation of the liquid. Especially if you have a system with elevation changes, you know from looking at your head data sets how much of pressure, so head, you still have left for overcoming a certain elevation. So if I select these one, and by the way, we also added these new ones over here where you can also plot your friction factor and your Reynolds number, which may come in handy. Density and wave speed were already there, but they also come in handy sometimes if you want to know these specific data, but they're not by default on to save some file size. Right. So let's run that simulation. So now you have that dataset head, which I just selected. So it's now includes this dataset, and you see that, like for instance, when you have this this pipe bridge over here, where you have a rise in elevation. Let's take a profile plot. From here to the far end. So you see that your head data set will just continuously decrease. Well, if you compare that with pressure, of course, going up will reduce your pressure because of the hydrostatic pressure loss, and then you will have a pressure gain when you go down again. But yeah, the head data set, so the amount of head still left will just decrease all over your length as you lose head because of the pressure loss over your piping. All right. Some final thing I want to show you is the addition of editing elements in a table. So let's select, for instance, all these pipe elements, and you can click edit in table, and that gives you this overview, and this will actually allow you to edit all these fields one by one or simultaneously. Just select them all and change them all. But you can also copy and paste them to a spreadsheet editor. So if I say copy and open my Excel and paste them, so any spreadsheet editor, of course, and you can use that or you for your own reporting or own use in the spreadsheet. You can also make changes over here and then import it again in BOSfluids. So save to a table, so that's a comma separate file. Load, if you save that that spreadsheet to a comma separated file, and you can load these fields again into BOSfluids again. So that was a feature requested by some of our users, and hopefully they and you as well can make use of that in the future. All right, so basically this concludes the presentation part, and we'll take a look at some of the questions that came in.